So now we can move into the more general discussion. So we can address some of the other questions that have come up over the last 3 talks. Is there anything new that people want to broach right now?
Should I stop sharing my screen, Jim?
Sure. I guess one question that came up was about whether future Gaia releases would help improve any of the conclusions from Travis's talk. Travis, did you want to address that question? There was some chat about it.
Yeah, I can address that. I think so. I responded in the chat to that, and I basically said I think Gaia. I guess it's EDR3 that is going to be coming out relatively soon, and it's going to obviously provide more precise parallaxes. But at least if you're thinking about the jump from Gaia DR1 to the Gaia DR2, that was a pretty big jump in terms of just the vast number of parallaxes that were added. But I think EDR3 is going to, at least based on the information that's been provided, is going to improve parallax precisions, probably going to provide a few more parallaxes to various stars. And then also it might improve some of the calibrations in terms of astrometric calibrations and that sort of stuff. So I think overall, I think the improvements are going to be relatively modest. So I don't expect them to affect the overall Kepler stellar properties all that much. But if you're looking at individual Kepler systems that could potentially not have Gaia DR2 parallaxes, they might actually be available in future Gaia data releases. And so those, obviously for those systems, it's going to be more useful.
Okay, thanks, Travis. So I guess another question that came up is it dangerous to make conclusions about the timescale of mass loss, given that potentially both mechanisms can last for a long time, especially the core-powered mass loss? Yeah, so anything you want to say about that, Travis? A similar question I had is, have you tried slicing the sample in any other way besides, you just grouped it into young and old systems. I mean, is there anything else we can do currently to get at this question?
Yeah, so that I think is a very interesting question. Just in terms of, I think, the overall, sort of from an overall standpoint, just getting overall timescale constraints, I think, is just going to be important, especially if we've got good stellar ages and good stellar masses for stars, being able to slice and dice the sample and choose kind of more, localized areas of parameter space and being able to look at various trends as a function of those parameters is obviously going to be very, very useful. But I think, yeah, I mean, as you point out, actually differentiating between core-powered mass loss and photoevaporation is going to be, I think it's going to be difficult. If you look at them as a function of stellar mass, it's going to be difficult in that area of parameter space. So I think, you're really there. I can't remember the exact areas of parameter space where we could actually right now go ahead and actually differentiate between those two theories. It's some combination of stellar mass, incident flux, and then maybe seeing, like, for instance, photoevaporate, and then also getting planet masses, which is currently where we're a little bit limited right now. But yeah, there's a lot more obviously to be done, and I think I think especially, like, if we want to actually differentiate between core-powered mass loss and photoevaporation, getting, for instance, planet masses, because there is a proposed planet stellar mass dependence that is required for photoevaporation to describe a slope in the planet radius stellar mass space. And so because of that, if we can actually get planet masses and then say whether or not that's true, that might be some way, for instance, to differentiate between those two theories. But again, there's also, things are a lot more complicated in real life too. So, we can't forget about that stuff too.
Yeah, maybe I can add a few more things to what you said.
Go ahead, Helga.
Yeah. I also just would like to remind all of us, we have to be a little bit careful. I think the timescale thing is great. And I do think it's true that overall we should see a rise in the super Earths earlier for the photoevaporation on average than for the core part mass loss if we're looking at the same sample. I think we just have to be a little bit careful at this very moment when we try to compare the amplitudes to either of these two models, because you have to make predictions specifically for the stars and planets that you actually observe. Because if I change the location of my planets around a given star, I will change them. And both models, actually, I will change the timescales when I convert them from super Earths, from sub-Neptunes into super Earths. So I think right now we have to be a little bit careful. You know, we can't say, oh, one group predicts it's 0.6, and the other group predicts it's 0.8. They're roughly consistent, because those predictions were made for a very different underlying planet distribution that is in your stellar sample. So I think focusing on the time scale and where most of the population emerges is fine. But I think if we want to do a detailed comparison, we have to make sure we're comparing the same. We do it or make predictions either for a population that matches yours, or you bias correct your population, so we do it for a completeness corrected sample. But it's just a word of caution that when we cannot quite yet really compare these amplitudes to the predictions because we're comparing two different things. And then on a different note, I think you touched on all of those. So I think given getting masses, if you can get the underlying mass distribution, it takes away a lot of wiggle room. So you can nail down, especially a photoevaporation is much more sensitive on that than I think the core part mass loss. So you can really say no more tweaking allowed. So you have to come down on one side or the other of this idea. And I think the last thing is you would expect a trend or not a trend if you can just look at in 3D along the stellar insolation flux, because in the core part mass loss model, we would say it's really just the dependence is on the insolation or bolometric luminosity received, whereas of course in photoevaporation, it's the high energy radiation on top of that. So if with enough planets, we have a paper with James Owen in the works, with enough planets, I think we can try to test this, but again, I think it's early times. So.
Okay, thank you, Helka. We have another question from Lynn regarding the ages. Given the methods involved in reliance of the posterior distributions, how confident are you in the less than 1 gig year ages? And do you plan to check them using activity or rotation diagnostics?
Yeah, so that's a good point. So a lot of, I think a lot of the ages that we determine for these stars, right? They're posteriors and there are uncertainties in their posteriors for if you noticed back when I was showing some of my slides, a lot of the ages were clustered closer to the 1 gigayear range than necessarily, closer to the 200 megayear or so range, right? And so at least based within their uncertainties, you've still got a little bit of wiggle room where some of those stars could be on either side of that 1 gig year line. And same thing goes with some of the older stars, right? But I think there's obviously some power that we're comparing ages like to like. We're using the same exact homogeneous stellar parameters. We're using spectroscopic metallicities, which will break some degeneracies between stellar age and stellar metallicity. And so so yeah, and in terms of using so right now, based on the stellar ages that we've determined, we're only looking at some of the more massive stars because these are stars that we can get accurate isochron ages for. So starting to actually expand the sample of stars that are of lower mass and getting ages or gyrochrone ages for those stars. So, a lot of the work that Ruth ended up showing yesterday in combination with kinematic ages, all that sort of stuff can be useful kind of lower down on the main sequence. I think that sort of work is at least going to be able to give us a more like robust young planet sample. But again, where exactly you make that cut of, is it 1 gig year? Are we talking 750 million years? Where exactly that cut occurs can kind of depend exactly on, your exact parameter space. But But yeah, I think absolutely, especially for at least checking them on activity rotation diagnostics. So that is actually some work that I'm currently looking into, looking at the entire Kepler exoplanet host star sample and using a variety of different age diagnostics to get a more robust stellar age sample.
Okay, last question from Victor. What are good stellar ages and masses in this context? So to what precision do you define good ages and masses?
So I think stellar ages, good stellar ages are probably anywhere. So good stellar ages are usually where we, at least with isochrone ages, talking, on the subgiant branch, and they're usually 30% or so fractional uncertainties are typically pretty good if you can get those for stars on the subgiant branch through like isochrone ages, for instance. And in terms of good stellar masses, I mean, in this catalog, we ended up determining median fractional mass precisions of somewhere around 5%. And so, I've also done some work on the planet radius stellar mass diagram and actually seeing what are the uncertainties associated with that slope and what are the different predictions from various theories. And getting like 1% precisions in some cases might be required. But again, it's, I guess, good stellar mass precisions are, I guess, less in terms of that, probably less than 5%.
Okay. I have a question for Boris about the photometric modulation that you see from these unipolar inductors. So I'm guessing you're inferring that that's the spin period of the white dwarf. Certainly in that 5-minute system, it would have to be the spin period. But do we expect to see a signal at the planetary orbital period or the beat period?
In principle, yes, but as far as I know, hasn't been detected in at least GD356, which has the best data of all the systems. Yeah, you would expect that you should pick up a beat signal if you have sufficiently good data.
Do you know theoretically? I actually don't know. Theoretically, do you know where the amplitude modulation is suspected to be largest? Is it the spin period or the beat period or the orbital period?
Well, they have different physical mechanisms. So the spin period depends on the atmosphere of the white dwarf and how the spectrum changes across the surface of the white dwarf. I mean, that's not totally clear if those are temperature variations across the surface or if it is just the shape of the spectrum that changes because you have a gradient in magnetic field strength across the surface. How strong the signal of the planet orbit or the beat is, I really don't have any idea.
Okay.
So yeah, one quick addition which I forgot to mention is that the spin period of 5 minutes sounds extremely short, but if you have a giant planet and you accrete the envelope of the giant planet, the gaseous envelope, that would probably provide you with enough angular momentum to spin a white dwarf up. So it's not crazy to have fairly rapidly spinning white dwarfs if they accreted from a giant planet, and that would naturally then leave over a possibly conductive core that is still there.
Yep. And I suppose you could also make it by a white dwarf merger, and that merger can eject some material which maybe could conglomerate into a planet. That's certainly what's expected for that idea that's been thrown out for some of the millisecond pulsar planets. So
that's what is discussed in a follow-up paper on the Lee paper by Gaensicke et al. The problem, it's not impossible, but the problem with that is that these 3 white dwarfs that I showed, they have all relatively average lowish masses. And so they would very likely involve a merger of 2 helium cores. And then it's not clear if you actually get enough heavy elements to make a second generation planet out of it. So they're all just kind of standard average mass white dwarfs. There's nothing unusual about them, and kinematically they're also not unusual. So mergers can't be ruled out, but there's no evidence that these are mergers.
Mhm. Okay, thanks. So we have a question from Sam Grunblatt to Dimitri. If a planet could temporarily survive being inside or incredibly near an AGB star, could its orbit evolve similarly via this proposed chaotic tide method, or would other forces likely overpower that? Could a planet potentially survive inside an AGB star?
Probably not, unless it was a brown dwarf. And actually, this goes back to Tiago Campante's paper with astroseismology that I discussed yesterday. If that planet is actually if it's in the clump, then its semi-major axis is so small it would have had to be engulfed in the planetary envelope to survive. And the region of parameter space is so fine for that to happen, it's very unlikely. So it's based on sound physical arguments. I would say it's not possible.
I would also guess that if the planet's inside of an AGB star, even if it survives, that other frictional processes would act on a shorter time scale than the chaotic tides.
Yes, I agree with that. The AGB phase is typically much less than 1 million years in duration, and chaotic tides actually do they do take at least 1 million years, unless again you're in a very small region of parameter space.
Okay, are there any other questions for any of the speakers? All right, well, maybe we can move on to our lightning talks then.